Okay, so we introduced the fourth quantum numbers is MS. So as MS represents the spin direction of the electron. So, for example, in this way, so there are two electrons. They have the same spin direction. And we can say the MS number is 1, right? But in this case, what the total MS number? 0. Yes. So basically, for this we will show the magnetic properties. So they will offset each other. Okay. And for this, because they have unpaired electrons, so they will show paramagnetic properties. Okay. So basically, for some metal irons, they have magnetic properties, but for some metal irons, cations, they don't have magnetic properties. Okay. Now, for example, question. For iron 2+ and zinc 2+, which one is paramagnetic and why? So basically, you should write out their electron configurations. So iron efficiency is 26, right? And this guy is 30. And here you can here we can see their configurations 2A14 2, right? And then here is 2A18 2. Okay, like this. So for this, lose 2 electrons 14, right? And then lose this is 18. So which one is paramagnetic? And yes, because for this guy, it has unpaired electrons. But for zinc, it doesn't have unpaired electrons. So the iron is paramagnetic. Okay. Now we know all electrons have energy, and we can use this equation to calculate the energy. So in this equation, we can say that only the number n, right? But we know the L may also affect its energy, but the L, the influence of the L on the energy is very small. So basically, we only using n to calculate its energy. So, for example, here n, if n equal 1, so the energy just the R is constant, and the constant number is 2.18 times 10 to power of minus 18. Okay, and the unit is joule. And the first step. So basically, we know the electrons in outside orbitals have high energy. Okay, so if the electrons move from the outside orbitals to inner orbitals, and their energy will reduce, right? So they should release this energy, right? So this energy, this release energy can be like photons. Okay, so this is why some atoms can emit light. So can emit light, it means they release energy. Why they release energy? Because some electrons move from the outside objects to inside, to inner objects. And we also can use this equation to calculate the energy between the energy difference between the objects. And also, the light is emitted as the electron moves from one energy level to a low energy level, from outside object to inner object. And the energy is emitted or absorbed in discrete units. Discrete is means also quantum. So when the electron move from outside to inside, so it releases energy, right? But of course, some electron can also move from inside inner objects to outside objects, right? How to move the electrons from inner to outside objects? How? So release energy or give? Yes, we just give energy. So give the atom energy. So its electrons will move from inside inner object to outside objects. So the energy can be emitted or can be absorbed by the electrons. But it should be discrete units. What this means? This means, for example, it's like this ladder, right? So this electron can only from this ladder to this ladder. Okay, it's like from here to here. It can't like move from here to here. No. Okay, because it can only move from one object to another object. It can't just move from here between the object. No. Okay, so this is also called quantum, or like discrete unit. And we also can calculate the energy difference, the energy that the electron released or absorbed. Okay, so for example, we go, this is n equal 1, right? Here is n 2, n equals 3, 4, 5, 6. So basically, for example, the energy, for example, for this orbital, it can accept electrons from n equal 2, n equal 3, or n equal 4, right? So all these orbitals can, the electrons in these orbitals can move to this orbital. And also for this n equal 2, it can accept electrons from n equals 3, 4, 5, something like this. Now we can calculate the energy difference between the orbitals. We can use it this way. Like for example, if one electron move from outside to inside, it will give out, it will release the photon. The energy of the photon is equal to the energy difference between these two orbitals. So we can like EF is final orbital, and initial orbital. Okay. So of course, in this case, the final orbital is 2, right? Is this n equal 2, but the initial is n equals 3. So here we know the this is show the orbital energy. Okay, this. So finally, we can get this equation, right? So, for example, in this case, what is Ni initial? Ni. What is the Ni number in this case? 1? 3, yes. 3, yes. What is Nf? Final. 2, yes. And then we get this number, and we also know this is constant. So we can get the energy difference, right? After we get it, we know for each photons, its energy can be like h times c minus lambda. This lambda is wavelength. Wavelength, because it's emit light, right? So the light has wavelength. So then c is the speed of light, speed of light, and h is also constant. Is a constant. So you should know this before, right? No. In physical, no. Anyway, if you don't know, so now you should know. Basically, for all light, its energy can be used in this equation to calculate. So in this equation, h is constant, c is the speed of light, and this is this wavelength, the light wavelength. Okay, we will do the calculation later. Okay, now we just introduce the concept about how to calculate the energy difference and also how to calculate the wavelengths of the photons. Okay. Now we say we introduce, for example, this when electrons move from this octus to this octus, so they will release light. So this light we call Lemon series. Lemon series light. For this light, we call Balmer series light. Okay, and this we call Paschen series. This bracket series. So from this picture, we can see this energy difference is larger or this one. Which one? Which one is the largest energy difference? So first, second, third, or fourth? Which one? Yes, the first one. The first one, the first series has the largest energy difference. Okay, so basically, and the second one, this series is in this area, visible area, visible. So visibility means this light, we can see this light, right? We can see this light. But for this, for photons, we can't see. Okay. And here to show the this is to show the energy of different light. Okay. But we just when the light in this area, we can see with our eyes. So and this is Balmer series. Okay. So here we know why atom can emit light, and also why metals can can emit different light with different wavelengths, just because there are energy difference between the octaves are different. Okay. Now question.
Sorry.
Yeah.
Can you go back? Wait. AM radio waves and FM radio waves are different.
Yeah. Yeah, they're different. So basically, for this has low energy, and this in the X-ray. No, we use the X-ray in hospital, right? Mm-hmm. So they have high energy, and of course, if they have high energy, they will harm our body. Okay. Mm. Yeah. But this or this, okay. Mm. Now question. When cork is bombarded with high energy electrons, this means it gets get energy. So X-ray are emitted. So calculate the energy in joules associated with the photons if the wavelength of the X-ray is 0.154 nanometer. We know this constant, the constant. So basically, for light, so how to calculate? How to calculate is energy? Just using this equation, right? Equal h times c, this one, right? Okay, so we're just directly using this equation to calculate the energy of the photons Okay? We should know this, right? Well, anyway. So, yeah, and this is equals c is light speed. So we get this equation. So from here, we can say the h is constant, right? And c is the speed of light. You know, the speed of light is 3 times 10 to the power 8. And so divided by its wavelength, you know the wavelength, nanometer. So it's in nanometer, it means it should be times this number, change to meter. So basically, in the chemistry, and of course in physical chemistry, you always need to take care. There are the units of the numbers. The units of the numbers. Okay. For example, yeah, the constant, the unit is joule times seconds, right? Second, and the speed, meter divided by second.
J is joules, right?
Joules, yes. Joule is a unit of energy. Right?
Yeah, is it what in physics? It was doing chemistry.
Oh, physics. Do you remember last? I think it's last time we introduced nanometer. Basically, the nanometer, right? Nanometer is means time 10 to the power minus 9.
Is that
What?
Actually, I don't know that physics online.
Physical.
Physics.
Are
you sure?
Yeah.
I was saying. Relax. I was saying.
It's not.
It is really.
Yeah, what's the question?
Since I learned chemistry, I will also put in physics.
Oh,
I didn't know the way can design.
no. This is also chemistry, you know. Sometimes you can't just separate. Oh, what is physical? Well, this is physical. This is chemistry. No. You know, basically, for example, oh, you can say this is maths.
Exactly. Good to this.
But this is not maths class.
We all know physics and chemistry.
Yeah.
So basically, you should be careful. You should be careful. There are units. Okay. So for example, for the wavelength, you can only using this unit, nanometer. So you need to transfer the nanometer to meter, and then you can offset the units, right? And finally, you can get the unit is joules. Yeah, good.
What's the difference between joules and coulombs?
You there's some number. You should joules times something that you go call. Yeah. I don't know. I forget. You know, there's something you can use a different way to describe the energy. Okay. Question 2. Second question. So calculate the wavelength of photon emitted by a hydrogen atom when its electron drops from n equal 5 state
Just do this.
to the n equals 3 state. And also here we here you see we use this to constants. So this means if one electron from n equal 2 orbitals to n equals 3 orbitals, so we take the wavelength. So think about it. So basically, the first step, you need to calculate the energy difference between these two orbitals, right? So how to do it?
This is why we
Do you think who's turn? Your turn?
This one. So smart.
So smart.
More.
So easy.
No, we
Oh, you can discuss. Okay. You can discuss.
The girl.
Oh, the girl.
Ah, you didn't. So first step, you need to calculate the energy difference between these two orbitals, right? How to get the energy difference? I remember. See, right? Using this equation, we can calculate the energy difference between these two orbitals. So initial, final. So what the n I in here? 5, yes. F 3. Okay, so we can R is here, right? So from this equation we can calculate the energy difference or the energy of photon of the photons, right? So like this way, right? Because 5, so square of 5 is 25, and 9. Okay, so finally we get the number, the energy difference is this number, right? Okay, when you get this number, how to calculate the wavelengths?
Use the first one, yeah.
Using which equation? Okay. This guy, right? I said you do it.
So smart.
So basically, you should go here to show us your answer.
Sure.
Now it's easy, right? Now we get this number, and this is constant. And what is the number? Remember?
Yeah.
What is this number?
3 times 10.
Yeah, 3 times 10. This is the speed of light, right?
Yeah.
So okay. Yeah. So and then from this equation we get the wavelengths. We can use this equation, right? So move this guy to this side and then move this guy to this side. So we get this equation. Okay. And finally we get this. And also always be careful. They are units. Okay. So for example, here should also meter and also so we can offset the joules and also finally nanometer. Okay, this is a meter. Meter we can change it to nanometer. Okay. So any question for this? Now you know how to do this, how to answer these kind of questions. So basically, what we want to know the wavelengths, we must know the energy, right? The energy difference. And we can use this equation to calculate its energy difference. And then we can get the wavelengths of the light of the photon. One more. You know this. Using this way, so not only understand more, it also easy to pass this course. Yeah, basically this is like 30%, right?
Yeah.
So after you get this 30%, And then your attendance come every day, so like it's for 40%, you almost get like 65 or 69.
Yeah.
So in the final exam, if you just even get like 40 points or 50 points, you can still pass the course.
That's fine.
Right?
Yeah.
Because the final test is open, but you can't see each other. You know, you should come in stay in the room and just complete the book, and I give you the test paper, and then you can finish and then give me your answer. You know, so you even get really low scores in your final test, but here you get high scores, right? So you should welcome the.
Yeah. Okay.
You like the homework,
Right.
you know. Okay, yeah, homework.
You
say want to take a photo? Yeah, I will send you the PPT. Okay, so this is about the chapter 3. You still some time. Yeah, 50 minutes. It's a long time. Oh, okay. I know you are tired. You know, I'm more I'm tired than you know. I sat here for more than 1 hour.
The time remaining, you can use to copy.
But no, we have still more than 10 minutes, so we should just learn something. Otherwise, I can't finish this chapters, you know. Okay, chapter 4. So this was about the periodic tables, and also using the periodic table to discuss, to learn some atomic properties. So this will question about why some elements are solids. But of course, not all. We can get all the answers from this kind of questions, but you can know a little about the properties, not only the atomic properties, but also the element properties. Okay.
Good.
So here we will see. So first we can introduce the octet rule. Okay, and also introduce isoelectrics and shielding octets and so on. Okay. So here. So this slide this has show you the time people found these elements. So basically, most of the elements are in like blue, right? Green. Blue color.
Please don't start with your colors.
Or like yeah, color. Okay. So yeah. And you have to show the classifications of the elements. So here we can see this S and P octets elements are called representative elements. Okay, and this part is called transition metals transmission, and it's S nice and S nice, and then we also introduce them one by one later. Okay, so now we also know in one group, for example, in this group, so there are most outside the electron are filled in NS. We can NS1. You can write like NS1, right? For example, so 1S1, 2S1, 3S1, 4S1, and this group is like NS2, NS2. So that will show the similar atomic properties. So we also call them like group. Okay, and the rows are called puries. This side, for example, here is NS2, NP5, okay, and S2, NP6. Okay, now you know this, right? So here, the octet rule. Octet rule means 4 energy levels are very low energy. So what does this mean? This means if the atom has the full share, okay? So it means it has low energy. It has low energy, it also means it is stable. Basically, for the atom, if there are electrons have low energy, means they are stable. If they have high energy, if they have high energy, it means they must release some energy. And so this means they are not stable. Okay. So full energy level are very low energy. And we know that low-Bell gases. What is low-Bell gases? Here, this group we call low-Bell gases. Okay. Here we can say for the low-Bell gases, there are electron complexes NS2, NP6. So it's a full energy. It's full share, right? It's full share, right? So because they are full share, so they have low energy. So this means they are very stable. Okay, so these gases are gases, and these gases are very stable. And unlike other elements, basically they are active. They can react with each other. Okay. So atoms behave in ways to achieve noble gas configurations. This means atoms try to become full share. Okay. For example, oxygen. So we know oxygen is 2s2, 1s2, 2s2, 2p4. Right? So it is still, so here is still 2p6 is full subshare. Okay? So it is trying to become 2p6. So this means the oxygen it's very easy for the oxygen atom to get 2 electrons from other atom, and then become stable O2 minor anion. Okay? Because it gets 2 electrons, right? So it's 2 minor charge, 2 minor charge. And then for the fluorine, we can say it's 2s2, 2p5. So it can still accept 1 electron. So it tends to get 1 electron to become F minus 1, F minus charge. So this is stable. So F minus 1 is stable. So if neutral fluorine is not stable, it's very active, and it can react with other elements and then get 1 electron from other atom to form ions. This for we know there are no metals, right? But for the metals, we can say for the sodium, and it's here. It has 3s1. So basically, it tends to lose this electron, right? Oh, good. So yeah, become stable Na+1.
Yes.
Na+1. Okay, and also the magnesium also easy to get 2 electrons. Oh no, sorry, lose 2 electrons to form this. So this is about the octet rule. Okay. Octet rule just used for representative elements. So it's called, octet means A, right? Because for representative elements, they are outside electron configuration is SP something, right? SP. So SP we can know S has 2 and P has 6. Should be 6. So add the 2 add 6 equal A, right? So it's also called acted rule. So acted rule. So basically for the representative elements, for transition metals is more complicated. For these guys, it's more complicated. Okay, a little more complicated. But for the representative elements, so for the metals, tend to lose electrons. For the low metals, they tend to get electrons to form NS2 and P6. NS2 and P6. So it's called the octet rule. Octet rule. Okay. So now we can using this way to write the ions. To write the ions. So yeah.
Yes, previous.
Okay.
So there, when you say oxygen 2 negative, so the negative, you put the negative when it gains,
Yeah, it's gains electron.
put the negative.
Yeah, because one electron is one. It is negative charge. Electron. So do you remember we introduced
There where it loses.
the loose? Yeah. So the loose of the plus.
Yeah.
If they lose, they have more protons, right? But protons is plus charge, right? Neutron is 0, and the electron is minus. So and the number of electrons equal to the protons. So if they lose the electron, they have more proton. So it has plus charge. Okay. Yeah. So, for example, when these 3 elements lose 1, 2, or 3 electrons, they have the same number of electrons, right? So these cations are like called isoelectronic. Isoelectron. Oh, I think you mentioned later. So yeah, basically when they lose 1, 2, or 3 electrons, they have the lower gas outer electron configuration. Okay, and also for this no metals, they get electrons. Okay, so basically, for this group, they lose NS1 electron. So basically, they should +1 charge. Okay, and this +2. Basically, and for this, they lose 3. But for this, they tend to get, not to do, because it can also lose like 7 electrons, right? But of course, it's more easy to get 1 than to lose 7. You lose 7, of course, it's very difficult. So it tend to get 1, so it should minus 1 charge, and this get 2, get 3. But for this, sometimes, not because they have 4, right? So in some case, they can lose 2 or 3 or 4. But in some case, they can get 1 or 2 or 3 or 4. Yeah. But basically, yeah. Basically, they tend to lose. Sometimes can get one more. Okay. Okay. So from the atomic configuration, so we can understand some atomic properties. We can understand their properties. Okay. Okay. So basically, the electron. This is about the electron configurations of cations of transition metals. Okay. Yeah. So yeah, that's all for today. So